Okay, so we should see a little red dot in the upper left-hand corner of Zoom screen, which means we are recording. And with that, I will start time and hand over the floor to Group 11.
Awesome. Thank you. You guys hear me okay?
Yes.
All right. So we are Group 11, and we would like to present you My Little Bioreactor. So My Little Bioreactor was created for the requirements of the UF binary system, the UF biofoundry, and features 8 subsystems ranging from thermal control, ODFI, and dynamic movement, among the others pictured. So how does this bioreactor work? So the user inserts well plates and conical tubes and sets the parameters of the study and the desired culture media in the reservoir. And from here, the bioreactor takes over. The enclosure is then sealed and the translation system transports the liquid, gas, and optical sensing systems to regulate culture composition and take readings. Additionally, the culture media sits on a thermal plate and a shaker system to achieve the desired experimental conditions. And finally, the waste system sequesters and neutralizes residual biological materials to complete the culturing process. So some motivations for our design included reliability, manufacturability, and reduced costs. By reducing the complexity of individual components and in turn the overall assembly, we wanted our bioreactor to limit the possible failure modes and ensure a robust overall design. Through the utilization and combination of different OTS components and easily manufacturable custom parts, we wanted to ensure a straightforward production and access to our customers. And finally, we strive to create a modular design that featured less components with interchangeable customization, and while still ensuring full bioreactor capabilities, which circles back to our main goal of simplicity. Specifically starting with the subsystems on the enclosure features 304 stainless steel plates surrounding being the principal medium between the inside and outside of the enclosure, and aluminum frame bars fastened with M3 screws acting as the skeleton of the enclosure. It includes a hatch door that features an open entrance and access point for the customer to manipulate and access the inside of the enclosure with push locks to secure the sealing mechanisms.
As you guys can see on the right plate of our enclosure, you can find the 4 main components. On the top right is the LCD user display that will come with the driver board to handle RAM and will allow the user to control any other subsystems by applying certain commands. On the bottom right is our 1800 watt capacity power supply that will assist in wiring other subsystems. Bottom left is our twist emergency stop button that will allow the user to completely halt the entire experiment for whatever reason if an error occurred. And on the top left is our raised indicator light that will flash red if an error has occurred and green for on and off functions.
So specifically diving into the plain wall selection, the stainless steel enclosure. So one of the customer needs specified by the UF Biofoundry was that the outside of the enclosure could not be too hot to touch. So we found a source from an ENS document that stated that the highest outside enclosure temperature comfortable to touch for a user was 50 degrees Celsius. So we back solved using a plain conduction to get the nominal stainless steel thickness that we could get with the temperature buffer down to 40 degrees Celsius, just in case. And we found that result was 2.25 millimeters, which corresponded to a 12 gauge 304 stainless steel, which was 2.66 millimeters. And then finally, these are our customer mapping for the different requirements specified by the UF Biofoundry and how we met them.
All right, so next up is the thermal control system. So our thermal control system design is going to allow us to both cool up and heat up and cool down the well plate liquids, as well as test tube liquids. In order to do this, we're going to be using an off-the-shelf mini refrigeration pump with a cooling capacity of 455 watts, along with a resistive heating element, which are both going to be placed in the same compartment, which is going to be filled up with water in order to have a circulating water system that's going to circulate the water to a custom-made heat exchanger that's going to be sitting within the well plate. On the next slide, you will be able to see the exploded views of both the external assembly, which is a refrigeration pump with the heating element. And so Tyler can speak now.
So the overall temperature range for our system is between -16 and 100 degrees Celsius. But for the desired experiments, we will go as low as 4 degrees Celsius and also overshoot to 80 degrees Celsius when we're actually heating the distilled water. We are utilizing a OTS dehumidifier that will remove humidity with inside the sealed experimental chamber. And the water pump will be running continuously whenever there is a temperature change within our closed loop system. Next slide.
Yep, so here's an exploded view of our custom-made thermal exchanger. The way it works is we're gonna get a piece of ABS stock that's gonna be milled out with a very simple tool path. As you see there, it creates a serpentine channel for the water to circulate through. Then there's gonna be a rubber gasket that sits between that and a copper sheet metal piece. What this allows us is to have the ABS acting as an insulator with thicker walls to prevent all the heat from being lost to, let's say, the atmosphere. And instead, it's all going to be conducted directly through the copper sheet metal. As you can see on the yellow markings on top, that's where we're going to have the well plate sitting. And there's going to be a test tube rack that's also going to be getting heated up and cooled down through conduction. In order to measure these temperatures, control the system more reliably than whatever we can model now, we're going to be using two sensors that are going to be correlated with each other with their readings. One of them is going to be a contact temperature sensor that's going to sit inside the water, and that is going to regulate the temperature of the water itself. Well, the infrared sensor that you see there is going to be mounted on a gantry system that's going to be able to target the individual well plate slots or the test tubes and read their specific temperatures. That way we can correlate our overshooting to heat the water and then how long it's going to actually take to get the measurements. So next slide, please.
In order to verify our serpentine channel design, we utilized a research study that performed an energy analysis not only on serpentine, but also multi-channel heat sink designs. They use water as their cooling and heating medium, very similar to ours, and they determined that the temperature distribution of the serpentine path was much more uniform and also experienced a higher Nusselt number, indicating better convective heat transfer. On the left part of the slide, you can see our 1D models for our heat transfer rates, which further supports our material selection of ABS and copper. Next slide.
All right, so we performed an analysis in order to verify the requirement 24, which dictates that the culture's temperature is supposed to reach its set point in less than 15 minutes. In order to do this, we created a numerical analysis in MATLAB that would allow for a variable heat transfer rate to happen depending on the temperatures of both the water that's circulating throughout the system inside the reservoir and the liquid that's going to be within a 15 milliliter test tube. As you can see on the image illustrated above, that's going to be the representation for our 1D model of heat transfer from the circulating water into the borosilicate glass test tube. And that's been all modeled in MATLAB with all the values that are appropriate for this. And you can see the charts on the bottom left. One of them is going to be the temperature gradient for circulating water in the system for the water reservoir, where we have the heating element that's turning it on, making it reach a temperature of 80 degrees, where then it turns off and it stays at that temperature as it transfers heat into the test tube liquids, which is trying to reach from a room temperature of 27 degrees up to 70 degrees as our maximum load condition. And as you can notice in the bottom, at the beginning of the test tube gradient, how it starts off flat and then it tapers up and then it eventually converges towards 70 degrees. That's because both water systems, right? Like let's say you have the test tube and you have the water reservoir, they're both starting at the same temperature. So the heat transfer rate is going to be 0 until the water in that circulating gets hotter, and then it starts heating up the test tube itself. So this can be reached through our simulation in a time of 10 minutes and 31 seconds. And this is just a representation of all the requirements that we are meeting with the thermal system and their responding values.
Okay, so I'm going to be introducing the translation control system. So the purpose of this system is to be able to displace key components of our other subsystems of the bioreactor, including the fluid handling, gas management, and ODFI sensing. These components, we're going to be mounting them on our multi-purpose toolhead, which is located on our z-axis of the gantry system. How we're going to be achieving this X, Y, and Z linear motion is by using a lead screw gantry system. Every axis is going to have an M10 carbon steel lead screw with a 2 millimeter pitch, ensuring the accuracy necessary to target each of our well plates. All of our axes are going to be driven with a stepper motor, an LDO stepper motor specifically, with an installation class rating of H. Essentially, this installation class is going to provide the motors with the capability to operate in ambient temperatures up to 130 degrees Celsius. As you can see, our x-axes are both driven by a single motor by implementing a timing belt and pulley system, along with a belt tensioner. And the last key feature I wanted to mention is the use of end-stop switches. So we're going to be implementing end-stop switches at the end of all of our 3 axes. That way, when our gantry system reaches that point, our controllers will be able to know that we have zeroed the gantry.
Tomas, you're muted.
Tomas? Yeah.
Oh, sorry. I was trying to say if you could go back for a second to the previous slide. I wanted to mention the reason that we're doing one motor that's going to control both the guides of the x-axis is one of the concerns we had was originally we had 2 motors and we were going to try to control them simultaneously. And when we realized how difficult this was going to be, we still couldn't have a guiding rod that would enact on the separate x-axis rail, as there would be like a binding that would occur. So instead, we came up with a solution of using a timing belt, which is not going to lose its track, with a pulley system, and it's going to be fully tensioned, so it's never going to lose its position. And then everything else just uses the guiding rods made of stainless steel. That way it all stays balanced and it stays pretty accurate and maintains its rigidity. So here we try to calculate if the motors that we selected had the appropriate torque to move the entire gantry system. So once the gantry was loaded with all the tools, we were in the full assembly, we were able to grab its mass, multiply that by gravity. And then we were able to use that to find all the normal forces and combining with the friction of the lubricant that we're going to use. And this would, and the efficiency of the lead screw, I forgot to mention that. That would allow us to find what torque we're going to need for each of the 3 axes. And as you can see in the results on the bottom right, that's a requirement of the torque for each of the different axes. And then on the bottom underneath the image, you're going to see how much torque each motor can provide. So they all satisfy the requirement of having sufficient torque for the application.
Yeah, we also completed 2 other analyses. On the left side, we completed a the linear velocity required for a gantry system to move between each slot in a 384 weld plate, and ensuring that we can target each of our weld plate slots under 6.5 minutes, which is one of our customer needs. And after computing the analysis, we confirmed that our motor does have the RPM capabilities to achieve this. And another analysis we completed was a simple beam deflection analysis, where we confirmed that the nominal size we selected for our lead screw, along with the material that we selected, is going to be rigid enough and experience very low deflection with essentially the weight that is going to be carrying across the lead screw. Next slide. And then this is our customer needs mapping, and this is where we mention how we target each of our customer needs.
Okay, so the optical sensing subsystem is responsible for taking the optical density and fluorescent intensity measurements of the cell cultures. For our system, to take the optical density measurements, we're going to be having a light below the samples in the well plate, and then we'll be measuring the output as the light shines through the culture on the opposite side to determine what the optical density is. And for those, we'll be using 600 nanometer optical density filters, because that is the industry standard for taking optical density measurements. But these can be interchanged if another measurement is desired. The light source for the well plates are these very small pico LEDs. You can see those in the LED scale picture. And the reason we chose those was because these needed to be mounted below the well plate, which is in contact with the thermal plate. We wanted to prevent as much disturbance from the contact area as possible, so we chose these LEDs. And then as for the conical tubes, we'll be using 3 millimeter high intensity warm tone LEDs, and these are mounted on the back of the test tube rack. These are, they have over like 95% relative intensity at 480 nanometers, which you can see in the graph on this slide. And that just means that they will be sufficient to provide the light for these measurements, and they also won't be lethal to the cells. because the lethal wavelength for cells is around 300 to 350 nanometers. And then since the conical tubes are not usually filled more than 20% during an experiment, we've enclosed the section containing the bottom more than the top because we wanted to reduce the amount of ambient light that could be affecting the readings. And then the reason for the color of the rack is because we learned that fluorescent intensity measurements, especially in test tubes, would be very difficult to achieve. So by having a black background, this can highlight the fluorescence being emitted by the cells, but using black can also have a risk of absorbing too much of the fluorescence. So we went with a dark gray color to hopefully gain the accuracy that we want in the test tubes, but also prevent too much of the light from the cells from being absorbed.
Our optical sensing tool is designed for easy repair and customization by the user. The tool will be translated via the gantry system over each individual well or tube location. There are two identical surfaces on the tool. The bottom surface will perform measurements on the well plate, and the lateral surface takes measurements from the side of the test tube. For optical density, the central 600 nanometer filtered ambient light sensor performs OD600 measurements using the light transmitted from behind the samples. For fluorescence intensity, the tool also holds several filtered LEDs which provide the incident light to be absorbed by the fluorophores in the sample, which then transmit light directly to the specifically filtered ambient light sensors. There are 4 different sets of filtered LEDs and ambient light sensors to provide a means of various FI measurements to be taken, depending on the needs of the experiments conducted by the user. Next slide, please.
And then on this side, you can see some of the detectable fluorophores will be able to, I guess, allowed to be detected based off the filters we selected. So this is just the distribution we have, but like Sergio said, this can all be altered depending on the experiment that you would like to do. And here's just the customer need mapping showing how we met the requirements of the UF Biofoundry. All right, and so for our dynamic control subassembly, it's comprised of 2 main components. The first one is the dual axis guide rail system, which will provide the rigid support for the loading that is being imposed by like the cell culture plate and the thermal plate that is going to be stacked on top of it. And then the second component is the system of driven kinematic linkages, which will be moving the shaker plate along these rails and creating the movement in the shaking patterns required by the customer.
So a shaker is a critical component of our bioreactor because it plays a large role in fostering cell culturing and preventing cell death. Shaking cultures promotes generative cell growth in many ways, the foremost of which is oxygen aeration of the culture medium. Through our research, we discovered that orbital shaking is definitely the most vital shaking pattern in cell culturing, and we referenced various sources and performed aeration calculations seen here to help determine our shaking patterns. These ranges are directly determined from the various volumes and shapes of the volumes that need to be agitated. Go to the next slide. We used a software called Linkage to simulate our shaker kinematics to achieve our desired shaking characteristics. We iterated through various combinations of these 4 variables until we converged on a setup where no linkages were mangled or broken and a satisfactory and physically possible design was achieved. Next slide. So as I just mentioned, we wanted to be able to achieve various shaking orbit sizes, and this was vital to effectively shake the wide range of well plates and conical tubes that our bioreactor can handle. To achieve this, we needed our linkages to be adjustable. Our current design on the right features fully adjustable linkages. The primary linkage, which is responsible for setting the orbital diameter, features tick marks and a knob to let the user easily adjust the orbital diameter. Next slide. So here we have a closer look of the primary linkage. It uses a custom female rod end and lead screw to adjust its length. And we chose to make custom rod ends throughout our linkages to reduce their size and to ensure that the female rod end's outer surface was controlled since it serves an important purpose, constraining its rotation. Next slide.
And then on this slide, you can see what the user would see when they are trying to adjust the primary linkages. This is what the view would be if the hatch was open and you were standing in front of the bioreactor. And then this is the view that the user would see if they were attempting to adjust the secondary linkages. And then on this slide, we have some calculations to justify our motor selection. To fit with our hedgehog concept of simplicity, we are using the same motors as the translational control system. And these are the calculations we use to spec these motors for the load case that we'll be undergoing with the shaking system. And these motors are very similar to the well-known NEMA 17 stepper motors, except they have H-class insulation, which is one of the highest insulation classes of motors, and it allows us to operate at a higher ambient temperature as well as improve the overall motor life when it's operating at lower temperatures.
So when analyzing the dynamic control system's failure modes, the worst load case was generally when the system was shaking orbitally at its highest frequency and largest orbital diameter. So we represented this orbital shaking pattern as sinusoidal motion, and that allowed us to calculate the peak acceleration at this load case. We performed failure analysis on many of the shaker components, but we determined the weakest link was this steel pin highlighted in blue, which couples the adjustable knob and the custom lead screw in the primary linkage. And even this pin safety factor was around 9, which exceeds the endurance or fatigue limit of steel components, meaning that no further fatigue analysis was required and we could assume infinite life.
And then here's just the slide with the customer need mapping for the dynamic control system.
Awesome. So next is the fluid handling system. And the fluid handling system is composed of 2 different parts, a distal portion and a proximal portion. The distal portion is the one that interacts with the well plates and conical tubes, and the proximal portion is the one that composes the pump and the selector valve as well as the reservoirs. As you can see on the distal portion, it features a miniature linear actuator and a PPS-Y connector and a custom pipette. And then you can see the ODFI tool for reference, as this is mounted on the multi-tool tool head. And on the proximal side, you'll see the stepper motorized mini syringe pump, our 10-port selector valve, and our 500 milliliter beaker reservoir. Focusing on the distal side, this distal side is the primary component that dispenses the culture media and other fluids into the well plates and test tubes. So the first point of concern was the point of importance was the pipette length. So the pipette length needed to reach the bottom surface of the conical tube, the longest conical tube, which is 120 millimeters. So we increased the length to 125 millimeters. As you can tell, that's a long pipette, and because of this, we encountered the problem that the pipette, as it's doing fluid handling, it could interfere with the ODFI system specifically because it was also mounted on the tool head. And it would interfere with its readings as the ODFI tool head had to get really close to the well plates. So what we did is we mounted a linear actuator to retract the pipette, and the linear actuator had a stroke of 100 millimeters, retracting the pipette to an overall length of 25 millimeters, which would allow the ODFI system to take its readings without any interference. Additionally, we did a Reynolds number calculation on the exit diameter of the pipette head to ensure that the customer need specifying no aerosols was met by achieving laminar flow.
So here's our pump and valve system. To further understand how they work together, and we included a visual, but essentially we are going to be using an off-the-shelf multi-port selector valve that is going to be coming in a 10-port configuration. 2 of these ports are going to be used as our output ports. One is going to be connected directly to our pipette, as we previously mentioned on the last slide. And then our other output port is going to be connected to a waste container. The rest of the 8 are going to be used as inputs. Our customer is going to have the flexibility to use up to 4 cell culturing media. We're going to have several different sanitation or waste management fluids, and one of the ports is going to be saved for air. The pump and the valve are selected through this inner port as it shows there. And the pump is going to be responsible for creating a pressure gradient that is going to be able to extract liquid from the desired reservoir to then dispense it through the pipette, or vice versa. So we completed a Hagen-Poiseuille equation analysis where we found the necessary pressure gradient to ensure that at the exit of our pipette, we can have the desired flow rate of 225 microliters per second to 300 microliters per second, which is one of our customer needs. And at the result of our analysis, we found that we needed to create a pressure gradient of 0.065 megapascals, and our pump that we selected can operate up to 1.2 megapascals. It also has a 20 milliliter aliquot volume, and it's going to be running with an accuracy resolution of plus or minus 0.4 microliters. And this is similarly as before in our customer needs mapping slide, where we go over how we meet all of our needs.
The waste management subsystem is largely integrated into the fluid handling subsystem in that the fluid pump and selector valve transports waste and disinfecting fluids. Important aspects of the My Little Bioreactor are the material selection for the pipette and containers to be autoclavable, such that they can be reused after disinfection and sterilization. Though it might be easier to go with the common practice of single-use plastics, our team values the cost-effective and environmentally friendly route of autoclavable and reusable materials such as glass, and polypropylene. Next slide, please. The primary disinfecting fluid that our bioreactor uses to neutralize waste on surfaces is isopropyl. Isopropyl has a relatively short contact time and is effective at neutralizing waste in most experiments. However, should an experiment involve bacterial spores, a sterilization fluid like formalin must be used to effectively neutralize waste on surfaces. However, this is a rare use case. Next slide, please.
So the disinfection operation utilized by our bioreactor has 6 main steps. First, the fluid handling system will suck up the liquid waste from the well plates and conical tubes and transport them to the waste container. Next, the fluid handling system will inject the used well plates and conical tubes with isopropyl. Once it does so, the syringe pump will fill itself with isopropyl, and the pipette tip will submerge itself into a conical tube or well. And at this point, the entire system will be sitting in a holding pattern with all wetted surfaces exposed to isopropyl. Next, the contaminated isopropyl will be pumped back into the waste container, and gas will then be used to purge the fluid handling system to evaporate all residual isopropyl. Then the autoclavable polypropylene waste container can be disconnected and autoclaved to neutralize any remaining biological agents. Next slide. To evacuate gaseous waste, a hatch over the side fan, as well as a hatch at the top of the bioreactor, will be opened manually. The fan will begin to pull outside air into the bioreactor, flushing it up through the top vent into a fume hood or biosafety cabinet. And the front hatch can also be opened for additional aeration. Next slide.
And finally, this is just the customer needs mapping for the waste management system.
For the gas management system, we are using 6 separate solenoid valves to control the injection of gas. This was chosen not only based off their lightweight and compact design, but also for their fail-safe design being normally closed. In order to utilize the fluid handling system, these 6 lines needed to lead to a gas manifold so we can have one outlet. The 6 solenoid valve is actually going to be used for helium so we can purge our system. The outlet of the gas manifold is leading into our first sensor, which is our pressure transducer, which will give the user feedback on the pressure within the gas lines.
Following the pressure transducer is our pressure relief valve, which simply allows any relief of any excess pressure. Following the pressure relief valve, our high silicone temp tubing will then lead to the mass flow meter, which allows the user to know the composition of gas entering. Then our tubing will then feed into the Y connector that was previously discussed by the fluid handling system. Here we have our silicone valves that the test tubes will utilize. This is basically helping the gas management subsystem take care of one of our customer needs that basically states the want to maintain independent environments for our test tubes. As you can see in the image, there's 2 cross-hatched valves located on the top surface. On the right is our pipette injection site, which is where the pipette will enter to inject the necessary gas. On the left is the pressure relief cross-hatch valve, which again is simply to relieve high pressure within the system.
So in order to utilize the Y connector from the fluid handling system, it required gas management to basically decrease the diameter. And we wanted to ensure that there wasn't a substantial pressure change in this part of the system. So utilizing a continuity equation with given velocities, we turned into the Bernoulli's equation, and we found the pressure difference between this change in diameter to be pretty minimal. Next slide. And here, similar to other subsystems, is our customer need mapping, where we quantify each metric. Next slide.
And then on this slide, you can see the controller and the DAC we plan to use to support our bioreactor. Specifically, we'll be using a LabJack T7 DAC that has 86 analog and 23 digital input-output slots. And this will be controlled by a Raspberry Pi computer. The reason we chose the Raspberry Pi was because it can be directly connected to the internet and it can run a variety of operating systems depending on the needs of the experiment. And then the supported components you can see on this slide for each subsystem are here.
So we broke down our costs into 3 main components. We have OTS materials, which you're going to buy. Then we're going to also be, for all the custom solutions, we're going to do materials and an estimate of the manufacturing costs. And this is how it breaks down.
The My Little Bioreactor sports many unique subsystems that each demonstrate their ability to effectively complete the tasks that they set out to accomplish via simplified solutions, from the serpentine fluid thermal plate and kinematic linkages to the multi-filter FI sensors and highly integrated fluid handling. Each subsystem comes together to form a bioreactor that proves itself to be a design that would expose Mech Design 3 students to a wide breadth of challenging and engaging engineering concepts that they would be tasked with bringing to fruition. With subsystems that work well because they work together, we believe the My Little Bioreactor is an excellent candidate for UF's new Industry 4.0 biofoundry. And for that reason, we hope you'll make the My Little Bioreactor your little bioreactor.
Okay. Clever ending. I like the rainbows too. You guys know that. I expressed my love for the rainbows previously. Okay, so let's open the discussion and ask our panelists if they have any questions.
So can you guys go back to your fluid control system real quick? I know I said I wasn't going to be here for the roast, but you guys got done early. So now, I guess it was your, I'm sorry, not fluid control, gas control. My bad. Sorry. Gas is also a fluid, in my defense. All right, so what's the purpose of the, you kind of glazed over real quick. What's the purpose of that pressure transducer?
To give live readings on the pressure in the system to the user to working connection with the mass flow meter, so we can regulate the composition within the system.
So you're measuring the fluid, the pressure of the fluid in the line, and then the mass flow meter to get the environmental composition.
Yes.
Is that necessary?
Well, we wanted to basically control the composition of the gas entering the test tubes to perform like separate and environmental conditions for each one. So based off what user picks for the gas entering the system, the mass flow reader will basically regulate what's entering each specific test tube.
I guess what I'm asking is, do you really need both sensors? If you have a mass flow meter, do you need a pressure?
Probably not. No, I see what you're coming with. Yes. True.
One of the things in engineering design is you're not done designing when there's nothing left to add, but when there's nothing left to take away.
True. Gotcha.
So that, and then also the PRV is it actually going to blow off at a low enough pressure? Because if it's rated to 300 PSI, what pressure do you think your system's going to get to?
Well, that was the max capability of that pressure relief valve, but there was settings low enough that wouldn't be able to relieve pressure if the system reached a certain point.
What pressure? Like, what's the lowest pressure that PRV can hit?
I believe it was 30 PSI.
What's the pressure coming from your wall or from your supply?
We assume 15 PSI.
Is that gauge?
Yes. I'm hoping it's gauge.
Yeah.
So if you have a pressure relief valve that blows at 30 PSI for its minimum setting and your supply is only at 15 PSI, what's going to happen?
Nothing. No, it's design flaw. I agree. Good point.
Cool. Sorry, I've been looking at, so my life at SpaceX was valves and regulators. So I see this and I'm like, ooh, great. Finally,
Yeah.
something I get to jump into.
I appreciate the feedback, definitely.
Yeah. So, all right, cool. I'll let other people take over now that I've had my couple of pokes.
All right, I'll jump in. You gave some details on the fluorescent intensity and some factors affecting that. Where did those details come from?
Like specifically like the color of the system, or like what details?
Well, you
We
had talked about
a variety of like sources.
like some of the practicalities of doing the measurement.
Right. So we've made it available to have up to 4 different arrangement of fluorescence intensities, like measurements, so that the user can detect up to 4 potentially fluorophores if their experiment requires them so, or if they just want to detect different. The reason for that is so you can actually like see what live cells might be in there, or other the words fluorophores that you can like absorb at different wavelengths and emit at separate wavelength. So we have 4 different.
Yeah, I guess what I'm getting at is did you discuss the practicalities of doing the measurement with the customer, or was that your own research, or where did that come from?
Oh, we had an initial interview given to us from the Biofoundry talking about what they were looking for, specifically with these measurements. From like the TAs of this class, they did an interview and they gave us the link for it. And then the other stuff we figured out, like specifically like fluorophores and like how the measurements would need to be made, that was our own research.
Okay, I'll say good. The more that you talk to the customer and understand how they might want to use your system and their experience with previous systems, the better. That's excellent information to guide your design. So good work on that. On your XY translation system, maybe I missed the early explanation on this, but why is it that you went with a 2 lead screw system for 1-axis translation instead of a lead screw and a slide?
Yeah, because we were thinking intuitively at first, like, all right, we need to use 2 lead screws because of the separation between them and the length of these carriages that run through the y-axis. And there's something called the binding ratio, where ideally what the maximum you could have is the length of like where the force is applied, in this case, which would be the motor torque driving it linearly. It can only be the distance that you're pushing against the other rail, which is the other x-axis lead screw, can only be twice as long as the carriage itself. So in this case, our carriages are 70 millimeters wide, and if we make them any bigger, it would lose its purpose, because first of all, you're adding weight and you're also, reducing its range. So instead, we don't want to have any binding, right? So if you have one motor and a guide rail on the other side, they're gonna kind of like bind. And what we did was we were going to have 2 motors originally, but we decided instead of going with 2 motors, we try to run both of them with 1 motor. So we have the pulley system in place, because controlling 2 motors at the same time, especially with their price, which is like on the lower end, any manufacturing imperfections could, have like different turn on voltages or like different startup times, wind up times. So we didn't want to lose track of that. And it would be easier to do this now.
I can definitely appreciate the single motor drive system. I think that's much preferable to trying to do it too. The other question I have on that is a materials question. You said those are carbon steel lead screws. Do you have any concern about those being in a hot, wet environment and being cleaned?
Okay, so they're not going to be. So what we're having a DuPont Teflon lubricant, which is nonstick. It's kind of like a dry lubricant, and they're used especially in these type of scenarios in 3D printers, for example, that use steel lead screw. So the lubricant will just be placed entirely in the thing, and since it's like not very viscous, it's kind of like a dry lubricant. It would stick there and would not come off. Therefore, you prevent corrosion by doing that. So that's what we had in mind, as to prevent corrosion.
Okay. Let's see, what else do I have? You showed a shaker plate, which looked like it was just a flat piece of glass or acrylic or something. How do you actually retain a well plate or a rack of tubes on there?
Yeah, so sorry, we should have listed that's just made transparent so you can see what's underneath it. It's an aluminum shaker plate. And if you go to the ODFI slide, you can see the rack that we have. This rack on the left side bolts through the thermal plate into the aluminum shaker plate.
Okay, so that's permanently mounted, or not permanently, but mounted to the table on the shaker.
Rigidly mounted, yeah.
Okay. Did you look at any natural frequency analysis of the components in your system? I saw you did a little bit of strength analysis, and I appreciate that you did that without a FEM. Did you look at any impacts of resonance in your system, or are you going to excite anything?
So we didn't perform any modal analysis, but we did make an effort to make the system as stiff, using like our engineering intuition to try to make the system very stiff. That's why we have like pretty thick motor mounts, and why the dual axis glide is pretty large compared to the rest of the system. But yeah, a modal analysis would definitely be like a next level step that could be taken to make sure that the no components get excited.
Yeah, I mean, nothing here stands out as particularly low frequency. I think you said you were hitting like 300 RPM or something, which is something like, well, I guess is 5 hertz. And there's nothing in your system that like jumps out at me as hey, I'm like a cantilevered beam with a heavy mass on the end, so I'm going to have a really low natural frequency. But just something to think about a little more rigorously than what's here. And then the one other question I had, you had your heating system looks like it is transferring heat just at the bottom of your tubes.
Yep, that is correct. Sorry, go ahead.
For a relatively tall tube with a small contact area, are you concerned about setting up thermal gradients in your system? If you're pumping in 80-degree water, are you concerned that you're gonna kind of cook the bottom of your tube without any sort of forced mixing?
Yeah, exactly. So the way we understood the system to work is, first of all, it's going to be through conduction, and the 50 milliliter tubes are only filled up 20%, so it's only going to be 3 milliliters, which is not as tall as some would expect at first. But also, as we understand it, the shaking system is going to be running continuously, except when there's like human interaction. That's what we've been hearing from like people maybe in like the MEC 3 lab, and that would provide like a very even heat distribution within like the liquid inside the test tube itself. So you'd have like forced mixing all the time, and that would like basically provide like a very even temperature distribution, which is why the analysis that we perform works, because it does assume even temperature distribution as energy is pumped into the liquid.
All right, good work.
Thank you.
Okay, any other questions from our panelists?
Couple here. So I was looking at your XY motion system, and since you don't have a like linear bearing or anything on the x-axis, if I was looking at the picture correctly, do you think that that will still, the lead screws alone will provide your system enough constraint and rigidity without the linear bearings?
Tomas, you're muted.
Sorry again. Yeah, if you go next 2 slides. Yeah. Okay, so you see we have a deflection analysis where it would basically prove that we do have enough structural rigidity with a deflection of only 0.06 millimeters. So using a 10 millimeter diameter, we reduce the weight and the cost of having like a thicker lead screw, but at the same time, we do provide enough structural rigidity since the maximum distance between, let's say like a 3D4 well plate, the distance between the two well plates, if you're trying to target an individual one, is 4.5 millimeters. This would provide like no deflection at all. That would like be in the range of like it's going to get a misreading because it's going to be in the next well plate slot because of the deflection.
I think it's also important to know that this analysis was completed on the axis that is going to be experiencing the highest load, which what we consider to be like our weakest point of the gantry system, and that's going to be our y-axis. We also completed this analysis with other lead screws, nominal sizes, and this basically experienced a very low deflection compared to the next biggest one, which was an M20. And that's why we thought that our system will be rigid enough no matter where the gantry system is during whatever operation we're performing.
Yeah, it was a nice balance between weight, cost, and rigidity.
Cool. So you talked about your time estimation for the 384 well plate XYZ motion system. Could you go into more detail about what time simulation is? Like, does that include 3-axis motion for moving up and down over the plates or the tubes and things like that? Or is that just 2D XYZ system moving through the...
Well, it's a planar movement. So we're only going to be considering, since the well plate is flat, we're only be considering X and Y movement. And since both the X and the Y are going to be using the same motors, the same lead screws, they're going to be able to displace themselves in the same velocity. So the way the well plate is oriented, you have, sorry, I don't know if you can see because of my background, but you have all these different slots in a line, and then you got to go to the next line, the next row. And so that way you can move like from one well plate to the next in the time that is required. Then you can move up one row, which is going to be the same distance. So the same velocity in the y-axis this time. And then you're going to go down the x and then again. So that way the velocity works for all applications.
Also, this customer need was specifically focusing also on optical sensing, like optical sensing's ability to perform readings on each of our well plates on a 384 well plate, under 6.5 minutes. So that's why kind of translation ODFI took over this customer need. And that's why we're only focusing on the XY plane motion, because ODFI doesn't need to be raised or lowered when changing between each slot. So this analysis also allocated some time for an ODFI reading, and then basically, essentially, since it's 6.5 minutes, we're estimated about 1 second that we need to move from each slot to from one slot to the other, and we allocated about 0.2 seconds for the ODFI to complete its reading. Therefore, about 0.8 seconds for the translation to move from one slot to the next. And that's kind of the backbone of the analysis, but that's why we also only did it in the XY plane, sorry.
Okay, cool. Last question here. For your heating and cooling system, do you have any, that's going to be mounted on the shaking table, correct? So it's going to be moving around?
Yep, that's right.
Any like sealing methods like O-rings, gas thing to seal heated water?
Yeah, so we have two considerations when we decided to use rubber as our gasket. Because first of all, we're considering the watertight seal. So as you can see, it wasn't finished in this model, but we do have bolt holes in a lot of different locations that are going to provide sufficient clamping force for a watertight seal. And when we go from like, let's say a cold water to hot water, we have to consider the thermal expansion of the system, right? So we have a very big heavy mass piece of ABS, which does not expand at the same rate as a thin copper sheet does. So what we're going to do for this is all the bolt holes that are going to be placed on the copper sheet are going to be slightly larger than what is required for the, for the bolts. So we're going to have these rubber washers, which are going to help when you want to damp any thermal expansion from the copper sheet to prevent any kind of like buckling from happening when the sheet expands faster than the ABS sheet. So that rubber force is going to also dampen its expansion so that it can expand without causing any structural failure.
Cool. Great job, guys. Everything looks really good.
Thank you, Ryan.
Okay. We've got about 3 minutes left. So if there are other questions from the audience, we can entertain them now.
Yeah, I have a couple concerns, or actually one concern. On that belt drive system, did you look at the initial force you'd have to do to overcome the sponginess of that belt, and what loads were being done that you have to overcome on that remote lead screw?
So in this case, I was also thinking about that. And what we're going to do is we have our belt is going to be, it has like a steel backing in it. So it has a bunch of steel wires that run through it. Kind of like like a car's timing belt, so that there's no, as you mentioned, like the sponginess or the deflection that you could have with the belt. That way they would keep always aligned itself.
Okay, thanks.
Yeah.
And then the last question is, you guys talked about flushing of the enclosure with air. Was consideration being done to filtering the air, or looking at what contaminants would happen if you flush a enclosure, and also the biohazard you might be introducing to the lab when you allow the flushing of the air out?
Yeah, absolutely. So if you go over to the waste management slide, actually, next one. Yeah, this one. So the customer will be able to choose if they want to flush it with air, which obviously will be pulled from outside the enclosure, versus nitrogen or helium, which will be like more controlled. If they do choose air, we have a HEPA inline filter attached to our selector valve. So the air will be passing through a filter that's pretty standard in BSL2 spaces before entering. But still, that obviously also is a wear item that would need to be replaced. And if they did really want to control, what they were flushing the air with, because obviously that filter isn't going to control the humidity of the air necessarily, they could choose to opt for helium or nitrogen.
Okay, great answer. And how about a flushing of the air out of the enclosure into the lab space?
Yeah, so that would be pulling external air, but we're assuming, based off of conversations with our TAs that we had at the beginning of the semester, that the entire experiment would essentially be happening inside a biosafety cabinet, from what we understand. This semester was obviously interesting because we did everything from home, so we weren't able to go into a lab or really see what kind of spaces that these would be used in. But at the end of the day, yeah, external air would be coming in just to completely flush the system between experiments. But during the experiment, we did really want to control what was entering and exiting the enclosure.
Yeah, great answer. I forgot about the biosafety cabinet. And just one comment, your guys' slides seem to be very good resolution, high quality compared to other groups, and your rehearsal handoff from one person to the other was well scripted. It's obvious you guys put some work into that. Thanks.
Thank you.
Yeah.
Thank you.
Thank you.
All right, great. So we have just reached the end of our hour with the group. So let's wrap it up there so that we don't get too far behind with today's schedule. I'm gonna stop recording.